Hey everyone, how's it going, BYU Physics 220 students? My name is Orion Rust, and today I'm going to be going over a little bit over threads versus Stubbs forces. This is a model that's a little bit unique to BYU and especially Physics 220. So I'll run you through a basic and a brief introduction of things because this is conceptually pretty hard stuff. Electricity and magnetism is no easy class, so you're in the right place, and I'll take you through a little bit of these forces that we're working with. So the thread model is essentially that those particles um, at the microscopic level emit tiny threads. Now, just to be sure, this isn't 100% entirely scientifically accurate. This is just a way that we can conceptualize what's going on um, at a small scale. And it's easy for us to model it with mathematical equations. What's really happening involves math that's way beyond our level that you won't get to until you take, I think, quantum mechanics. But essentially, the thread model is that these particles emit tiny threads at the speed of light. And right here on this model, we can see that we have a head represented by a solid dot and a tail represented by a hollow dot. And the arrow shows the direction of the threads. And so each thread will travel along this dotted line. With positive charges, it travels away from the charge, and with negative charges, it travels towards the charge. And each thread is a certain thread length, L naught, and that's our thread length. And keep in mind, these are microscopic threads, and the amount of threads that are emitted per second is our number of threads. When we multiply that by the length, we get those two are proportional, not equal to, they're proportional to the velocity. Um, so we're given here our constants. We're given that the elementary charge is 1.6 times 10 to the negative 19th coulombs. For electrons, it'll be this charge, but negative. And then we're given our permittivity constant, which is 8.85 times 10 to the negative 12 coulomb squared per Newton meter squared. And these factor in really nicely to our equation. Our um, equation for the force of a thread, keep in mind this is for the thread, is E over E epsilon naught, the charge of our field particle times the length of our threads. And then this new right here is just our thread density. And when we're given those things, we're able to calculate the thread force or the force that the thread exerts. And when we get to electric fields, the electric field is um, simply put, the force of the thread without the charge. You just divide the Q, and that essentially becomes this equation, E over epsilon naught. Let me try again. That's kind of rough. We have E over epsilon times um, the length of our field particle. And notice that this is a vector quantity, so it's going to affect the direction of our force. Essentially, the same direction that the thread is heading is the same direction that the force exerts. And this is where we get our electric force from. Electric force is derived from this thread force. And so keep in mind these quantities are really important. And keep this equation right here, especially in the back of your head, because we're going to use it later on to derive another equation. So this is really nice when we have a stationary particle that's not moving. Things are pretty simple. It emits threads. Um, Positives, if we opposites attract, right? And likes repel. But what if we have another example where our thread is moving or our particle is moving? This gets a little trickier. When things start to move, we have to involve relativity, and it's kind of a pain in the neck. So, because threads are being emitted at the speed of light, when we have a particle moving that's also moving close to the speed of light, we have to involve a little bit of relativity. To kind of conceptualize it, I like to think of a person standing on a train. Now, if you're standing on a train and you see someone in a car that's going about the same speed, a- according to your frame of reference, the car isn't moving at all if you're going the same exact speed. And the velocity of the car relative to you as an observer is zero if you're going the same exact speed. However, if you continue, if the car is going a little bit slower than you, it looks like their velocity is negative because the train keeps going with you on it, and you're observing the car going backwards. But in reality, the train has a greater velocity. However, with light, when we're moving at the speed of light, things are really tricky. We're given our constant for the speed of light. I'm going to look it up so I'm not teaching false doctrine. I have our speed of light is about 2.9 times 10 to the 8 meters per second. So it's ridiculously fast. Our speed of light is given by the letter C, and the speed of light is constant. So if you're moving, going back to the train example, if you have a flashlight and you're moving on a train, and the train is moving at 500 meters per second, and you shine your flashlight, you turn it on, and the light beam starts going at 2.9 times 10 to the 8th meters per second. We'd expect for the light to move an additional 500 meters per second, or however fast the train is going. But actually, light doesn't do that. Light continues at 2.9 times 10 to the 8 meters per second. And again, it's super hard conceptually to think of why this happens. I'll admit I don't 100% understand it myself. Um, but what we can learn from this is that light, no matter what, is constant. The speed of light is constant, and that's where relativity comes in. Now, when we have things moving, particles and threads moving at the speed of light, we need to make relativistic corrections. This model that we have right here is a particle moving and it's emitting threads. Moving back to our previous model, the heads are the filled in parts and the tails are the circles that are empty in the middle right here. So our particles moving along here, along this red line, and the red lines show the path that the head has. Sorry, it shows the ray line between the particle and its location. Now, the little lines, if we zoom in right here, we can see these little blue lines. These are what are called stubs. So the stubs are essentially relativistic corrections to our thread model. Because we're going at the speed of light, things are kind of tricky. And the Physics 220 textbook will take you through this wonderful example of how geometry is kind of weird with the speed of light. But essentially, all you need to know is that threads are relativistic corrections for our thread model. And threads represent the magnetic force. So our magnetic force, and our magnetic force is given by this equation right here, which is the elementary charge over the permittivity constant, the charge of the field particle, and then the thread density. And then this B right here is essentially this beta right here is our velocity, particle velocity divided by the speed of light. And notice that it's a vector quantity, and so it's important what direction our particle is heading. And the S vector right here represents the direction that the stub is headed. And what we can learn from this, from the right-hand rule, is we can learn, if you've taken linear algebra, you know that the cross product of um, of perpendicular um, perpendicular vectors is another vector that's perpendicular in the z direction. And so using the right hand rule, right here, we have our hands. If you can see my camera, we take our thread, the direction of our threads, and the velocity of the particle. And wherever our thumb is going, if it's a positive charge, we use the right hand rule. If it's negative, we use the left hand rule. And wherever our thumb is pointed, that's going to be the direction where the stubs go. And so you can see here, the stubs are essentially a vector product. The the force of the stubs, excuse me, the force of the stubs is a product between the velocity and the direction of the stubs, the direction that the threads are headed in. So we use this right here. Usually our particles and our threads move at the speed of light or at a fraction of the speed of light, pretty dang close. Um, and yeah. Now going on to our final part. When we combine the two equations, we get what's called the Lorentz force law. And the Lorentz force law is best described as the charge of our field particle multiplied by the electric field plus the charge of our field particle multiplied by the velocity of the field particle and then times the magnetic field. And remember, we got from this first page right here that our electric field is our electric force divided by our charge. And here we can also write, we use the letter B to represent the magnetic field. B is equal to the stub force. B is equal to the stub force divided by the charge of the field particle. And so essentially we get this really nice equation here that tells us about the force. And notice um, we have our vector dot product right here of the velocity of the field particle and the magnetic force. And our total force that's going to be acting on this particle, it comes from the electric, which is these two terms right here, and the magnetic force, which is right here. And a way that we can simplify this to make it a little bit easier is thread particles are emitted at random, and they're kind of all over the place. However, when we line them up really nicely, we make our electric field lines. This makes it nice and simple conceptually to think about. And so that's when you get the diagrams like this with the arrows on them, and they're all kind of in one way or another representing the motion of the representing the direction of the electric field force. Right here in this diagram, we also have on the left, it's a more realistic model of what's happening with our particle. We have the blue lines represent the path that the threads follow, and then our red lines right here represent our stubs. And when we line them up, it looks really nice actually to look at. And from there, we can do some more calculations and more mathematics. But hope that helps conceptually understanding the difference between threads and stubs and really getting the thread model under your belt because it's a helpful way to help us understand how electricity works, what's going on under the hood, and we can derive some equations from there to mathematically model what's going on. Anyways, hope you have a good one. Take care.